If you haven't watched part 1 of this yet, go do that. Today we're talking about the pitot-static system, as well as some problems you can run into with it and how to fix those problems. In the last video, we talked about the electrical system and the vacuum system. The electrical system is powered by the aircraft's battery, and the vacuum system is powered by the outside air that is sucked in by the vacuum pump. Well, the pitot-static system also brings in air, but rather than bringing it in for powering gyroscopes, it instead measures air pressure to give its designated instruments their proper readings. Again, while the vacuum system physically pulls in air to spin and power gyroscopes, the pitot-static system measures air pressure to calculate speed and altitude. Now you can probably guess the 3 instruments this system powers because they're the only 3 of the 6-pack we didn't talk about last time. But in case my videos are just that non-engaging and you don't remember which ones we covered, the pitot-static system oversees the altimeter, the airspeed indicator, and the VSI. So how does it work? Well, in terms of physics, air has mass. When you move through it, the air exerts pressure, hence the term air pressure. There are 3 different types of air pressure that are relevant here, which are static pressure, dynamic pressure, and total or RAM pressure. Now, static pressure is just the ambient atmospheric pressure that exists whether you're moving through it or not. It decreases as altitude increases. Dynamic pressure is the extra pressure created by motion through the air. This pressure increases with airspeed, and that leaves total pressure or RAM pressure, which is the sum of static pressure and dynamic pressure. So just the 2 added together. Now I'm going to divide this system into 2 parts, which is the pitot and the static. The pitot portion begins with the pitot tube, and the static portion begins with the static port. The altimeter and the VSI use the static port, while the airspeed indicator uses the pitot tube and the static port. Alright, first let's take a look inside the airspeed indicator. As you can see here, the instrument begins with the pitot tube. The pitot tube brings in ram air pressure through the small hole at the end of it. This ram pressure is fed up to the pitot connection. Static air pressure is brought in through the static port and fed through the airspeed indicator's static air line. Both the ram air and static air travel to a diaphragm that expands and contracts based on the levels of ram and static air. Just picture the movement of an accordion. When the ram pressure becomes greater than static pressure, the air inside the diaphragm pushes outward, causing it to expand. As ram pressure decreases, the diaphragm contracts. Think of it this way. As airspeed increases, the diaphragm slowly expands with it. And inversely, as airspeed decreases, the diaphragm slowly contracts. Can you think of something else in the airspeed indicator that moves with airspeed? The needle, right? Well, this isn't a coincidence. As the diaphragm expands, it turns rods and levers that are connected to the needle. So essentially, when the aircraft speeds up, the air pressure expands in the diaphragm, turning the needle to the right. When the aircraft slows down, the diaphragm contracts, turning the needle back to the left. And this is how we get our airspeed readings. While it may look complicated, the process is actually fairly simple. Alright, now let's take a look at the altimeter and the VSI. The vertical speed indicator actually does not directly measure vertical velocity. It measures the rate at which static pressure changes over time. Since static pressure decreases as altitude increases, the VSI simply converts pressure change per second to feet per minute. That's it. If you look inside, the layout looks fairly similar to that of the airspeed indicator. You have your diaphragm, all the levers and rods, and a needle. And just like the airspeed indicator, the diaphragm expands and contracts to move the rods, essentially moving the needle up or down. But you also have your case and calibrated leak here as well. So let's say you're in a climb. As your altitude increases, the static pressure decreases, causing the diaphragm to contract, raising the needle on the VSI. If you're in a descent, the static pressure increases because altitude decreases, causing the diaphragm to expand, swinging the needle downward. Whether you're climbing or descending, air pressure gets trapped inside the case regardless. The calibrated leak allows air to exit the case slowly so an excess of pressure is not built up, but still keeps air somewhat contained inside the case. If you're gaining altitude, the case is at a higher pressure than the diaphragm, causing it to expand. If you're losing altitude, the case is at a lower pressure than the diaphragm, causing it to contract. Put simply, all the altimeter does is it converts static air pressure to altitude. Atmospheric pressure, also known as barometric pressure, decreases as altitude increases. At sea level, pressure is high. As you climb higher, air gets thinner and pressure drops. The altimeter works based on this principle. It deduces how high you are from sea level based on the pressure outside. The outside of these aneroid wafers are exposed to the static air pressure. In a climb, static air pressure decreases, and therefore the pressure inside the wafers is relatively higher, causing them to expand. In a descent, static air pressure increases. Pressure inside the wafers is lower, causing them to compress. So, in a nutshell, climbing equals expansion, and descent equals compression. And the system is pretty consistent among these three instruments, the altimeter being no exception. Just look at the aneroid wafers as a substitution for the diaphragm that's in the VSI. As the aneroid wafers and the altimeter expand in a climb, the movement rotates gears and linkages, moving the needles to the right or upward. The opposite is true during a descent. Alright, so now hopefully you have a decent idea of how the pitot-static system works, but that can only help you so much when the system malfunctions or you begin to have technical issues up in the air. So let's finish out by talking about some problems you can run into and how to solve these. The two main ones that you're likely to run into are icing and blockages. Pitot icing happens when the ice forms on the pitot tube, blocking the opening that measures the ram air pressure. Since the pitot tube is what supplies total pressure to the airspeed indicator, icing can make the airspeed reading incorrect or completely useless. This is most prone to happening when operating in visible moisture if the outside temperature is 40 degrees Fahrenheit or less. Regardless of whether or not you notice icing, if you're in these conditions, turn on your pitot heating. As far as blockages go, both the static port and the pitot tube can be affected. Blocking in the pitot tube or static port can be caused by icing, insects, dirt, or tape left on during maintenance, in which case you know it's time to get a new maintenance guy. As far as the pitot tube goes, many pitot tubes have a drain hole on the back. If the front opening is blocked but the drain hole is still open, the ram air cannot enter the tube, causing the airspeed indicator to drop to 0 because the pitot line can no longer build pressure. If the front opening and the drain hole are both blocked, this creates a sealed pitot tube with trapped pressure. The airspeed indicator will behave more like an altimeter and read faster in a climb and slower in a descent. As for the static port, since static pressure feeds all three instruments, blockage here can affect multiple readings. If the static port is blocked, the altimeter will freeze at the altitude in which the blockage occurred, and the VSI will read 0. The airspeed indicator will read slower in a climb and faster in a descent. If the static and pitot are both blocked, the VSI will show 0 and the altimeter and airspeed indicator will be frozen. As far as solutions go, if the pitot tube is blocked, whether it be the main ram entrance or the drain hole, the best thing you can do is turn on the pitot heat. If the static port is blocked, use an alternate static source. Most training aircraft have a small lever or knob labeled alt static or alternate static source. This opens a valve that disconnects the static line from the blocked external port. Cabin air pressure is then routed into the pitot-static instruments. In the rare case that both the static port and the pitot tube are blocked, just perform both of these procedures. Sometimes even the alternate static source won't work. In this case, as a last resort, take a hammer and break the glass on the VSI, letting cabin air into the system. It's not exactly the same pressure as the outside air, but it's pretty close. And that's the pitot-static system. I know we covered a lot there, but if you can get a good handle on the systems we discussed, then you should have no problem on your knowledge test. And also, don't put a lot of pressure on yourself to fully comprehend and be able to recite every single thing I just talked about. All you need to know is the basics of how each of these instruments function. If you can get that, you'll have no issue. I'm also going to put a link in the description to a quiz I've put together for the vacuum, electrical, and pitot-static systems, and I'll include the answers at the end so you can check your work. For the next video and part 3 of this section, we'll wrap up systems and instrumentation and discuss the magnetic compass along with all that entails. As always, feel free to reach out if you have any questions and let me know in the comments what you thought of this breakdown, as well as subjects you'd like to hear me cover down the road. Thanks guys, I'll see you soon.